Okay, so we've been talking about atoms and elements. I don't know why this is showing. So a little bit about some important groups, and we're going to go through this pretty fast because you can read through it. Hydrogen is a nonmetal, and it is above or listed as in group 1A, but it doesn't really belong in group 1A for most cases because it's very different. It's actually can kind of be studied by itself. So it's colorless, and in its natural elemental state, it's a diatomic gas, which means it has a hydrogen and a hydrogen bonded together, so two atoms, diatomic. It's very low melting point and density, of course, because it's a gas at room temperature. It does react with nonmetals to form molecular compounds, HCl, H2O, of course, which is water. It reacts with metals to form hydrides, which is an H negative. That's what a hydride is. And a hydrogen with a negative charge. And when we look at H reacted with halogens, which is typically, we'll show that with an X. So chlorine, fluorine, bromine. It forms acids in water, and they will dissolve. Group 1A, which again, hydrogen is here, but hydrogen doesn't really belong there, are alkaline metals. They're typically soft, low melting points, low density. With the flame test, if we burn them, lithium will burn red, sodium burns yellow, potassium will burn purpley, violet. The big thing about them are they're all very, very reactive to give up their electron to form an ion. So sodium usually, in its elemental form, not usually in its elemental form, it's a metal, and that's how we'll call it, sodium metal. But typically it'll form the sodium ion, and that's how we see it mostly in nature. But sodium metal is its elemental form. Very, very reactive. They tend to form water-soluble compounds, and we usually call them salts. Usually you think a table salt is sodium chloride, but potassium chloride is also considered a salt. So salt's just a term in chemistry. They're colorless solutions when they dissolve in water. If we take something like sodium metal and we react it with water, we're going to form sodium hydroxide and hydrogen gas. And in fact, these compounds in the elemental form are so reactive that we really need to make sure that they're not exposed to water in the atmosphere, because if I take a chunk of sodium metal and put it in water, it will catch on fire. Because it's so exothermic, it releases so much heat that it causes combustion to happen. And then we have sodium hydroxide and H2 gas that's formed. And H2 gas, of course, is very stable. So we have to be careful with these, how we store them. They're typically stored in mineral oil because water and oil don't mix. So it creates a barrier from any water in the atmosphere getting onto the elements of sodium. Or potassium, also very reactive. Group 2A are alkali earth metals. They are harder. And in fact, I can cut an alkali metal really easily by just taking a spatula, a little metal spatula, and I can easily just cut it, scrape it. It's very, very soft. Alkali earth metals, however, are a bit harder. They're denser, and we're going to talk about that later, what makes them more dense. Like magnesium alloys are used in structural materials. As far as flame tests, you can still do flame tests with these metals, and depending on them, they'll burn different colors. You don't have to memorize what colors they burn. They are reactive, but they're less reactive than our alkaline metals. So our alkali earth metals are still reactive, but not as reactive. So they're not as exothermic when they're giving up their electrons. They form stable insoluble oxides, which is how we normally extract them. So oxides are basic, and they do react with water to form, depending on which metal. Beryllium doesn't really react too well, but magnesium will react and form steam. Calcium, strontium, and barium will react in cold water. So they do have some reactivity, but not as reactive as those group 1A ones. Another really important group as we talk about reactions are the halogens. Again, oftentimes you see this as X, just in general. They'll be shown as X in chemistry. So our halogens are group 7A. They're non-metals. They're already in group 7. They also exist as diatomic molecules like hydrogen does. Since hydrogen exists as H2, they exist as F2, chlorine 2, bromine 2, and iodine 2. But again, it depends. They can be solids, liquids, or gases. Fluorine and chlorine in their elemental form are usually gases, so you'll hear fluorine gas, and that's understood to be Cl2. Bromine in its elemental form is a liquid, and iodine in its elemental form is a solid. Later on, when we talk about these atoms, we'll really get into why they exist as diatomic molecules and not just as one atom. Right now, just understand they're very reactive in these elemental forms. Again, chlorine gas, very toxic. You don't want to be in the presence of chlorine gas without protection. You don't want to breathe it in. But we eat sodium chloride all the time. The chloride ion is very stable, not very reactive. They react slowly with water, however, bless you, but they will form an acid like HBr. They react with metals to form ionic compounds, and that's what we'll be looking at a lot in this class. And they also react with hydrogen, well, they form acids with hydrogen. So our strong acids are HCl, HBr, and HI are 3 of our strong acids. HF, however, isn't considered a strong acid. It doesn't completely dissociate in water, but it's still acidic. So when we're looking at our acids there, our strongest acids are strong acids from HCl, HBr, and HI from our halogens. So halogens are a group that we'll talk about a lot. Another group that's going to be really important, though not very reactive, are noble gases. That's our group 8A. They're all gases at room temperature, hence the term noble gases. They have very low melting points and boiling points clearly. And the big thing about them is they're very unreactive. So when we have something that's unreactive, we call it inert. It won't really react with very much. And we're going to use the noble gases to understand why our other elements are reactive. So the fact that they're very stable, and when something is very stable, it won't react very much, it's going to give us clues as to why our other compounds do react. So if we understand why they're so stable, it'll help us to understand why other compounds aren't. So it's very hard to remove an electron or give an electron to a noble gas. So it's not very reactive. And again, you don't necessarily need to memorize everything I just said. It's just to give you an idea of some of these. I'm coming. Sorry. I think the system wants me to update my iClicker software, and that's why it does that weird stuff. But I don't like scraping in the newer iClicker software. So that's why I'm keeping this one. Remember, this is the time you have left. We've talked about ions forming. How do we predict what's the most likely ions to form? It's a bit more complicated when we're talking about our transition metals. But for our main group elements, it's very easy to figure out which ions are going to form. Now I'm going to go through and give you the rule. But later on, we're going to really look at the atoms and understand where the rule comes from. So right now, we're just going to talk about the rule. We'll see how the periodic table can predict it. But later on, we're going to really understand where it comes from. So the charge on an ion if we're talking about the main group elements, can be determined from the element's position on the periodic table. And there's a reason for that, which we're not really getting into in this chapter, but we will later on. So metals we know are going to form positive ions. We already talked about that. They like to give up electrons. Our main group elements, our charge is going to equal our group number, the number at the top of the periodic table. And again, we're really going to delve into why that is later on, why that rule works. As far as our nonmetals, remember all of our nonmetals are in the main group parts. So for our nonmetals, they form negatively charged anions. They gain electrons. The amount of electrons they gain, the charge, we can figure that out based on the group number minus 8. And that 8 is going to be really important later on, which we'll talk about in more detail. So oxygen is in group 6A. So taking that 6 minus 8, we're going to get a negative 2 charge. So it gains 2 electrons. We're going to learn later the reason why is the goal of every stable compound is to get 8 electrons in its outer energy level. So that's where that 8 comes from. But right now you're going to know the rule. And again, all our nonmetals are in the main group, so this is going to work. And if we think about our group 8A, which is our noble gases, they're not going to form any charge. They already have 8 in that number. So 8 minus 8 would be 0. So we can figure that out looking at the periodic table. So looking at everything in group 1A, notice it forms positive 1 charge. Hydrogen can also form a negative 1 charge, so it's a little different. The other metals can't. Hydrogen is a non-metal. Everything in group 2A forms a positive 2 charge. And our metal in group 3A forms a positive 3. Now remember, these are metabolites. We're not really concerned about those. Then our nonmetals, starting with sodium, is in group 5A. 5 minus 8 is going to give us a 3 minus. So they form 3 minus. And so on. So we can use those. And again, our noble gases, they're not going to form ions because they're very stable and they don't react. Notice that everything in group 6A forms a minus 2 charge. Everything in group 7A forms a minus 1 charge. So again, you can use that rule. So looking at potassium, here's potassium. I have it in red. Potassium's in group 1A, so it's going to form a plus 1 charge. And we show that with our symbol K+. We look at sulfide ion. It's a metal. It's a non-metal. And it's in group 6A. So it will form 6 minus 8. It's going to be a minus 2. So a 2 minus charge. Again, notice with potassium, we don't show the 1. The 1 isn't shown. If we look at calcium, it's in group 2A. It's a metal, so it's going to form a positive charge. So it's going to form a 2+. And bromide is a halogen. It's a non-metal, so it's going to form a 1 minus. 7 minus 8 is 1. Aluminum is a metal, and it's in group 3, so it's going to form a 3+. Now the transition state ones, we don't have that same rule, so I won't be asking you about those right now. To determine which charge it forms, we need to know what it's bonding with, and we'll talk about that later. So we can't just look at the periodic table and say, copper is going to form this charge. I know copper can form a 2+ or a 3+ charge, but you need to see what it's bonding with to determine which charge it's formed. So you can't just get it from the periodic table. But for our main group ones, it's very simple. So looking at this one, of course, the answer is magnesium. Here's magnesium. It's in group 2, so it's 2+. Aluminum is a metal, so it's going to form a positive charge, but it's in group 3, so it's 3+. Sodium is a metal, so it's never going to form a negative charge. And fluorine is a non-metal, so it's never going to form a positive charge when it's giving up or accepting electrons to form ions. Now going back to what we talked about with atomic mass, we discussed isotopes, and we discussed the fact that our mass on our periodic table is based on the average mass of all isotopes in nature. So now we're going to talk about how to calculate that. Because we should be able to calculate that if we are given some information. So we generally use our average mass of an element's atoms for our periodic table, which is why none of the elements on the periodic table have just a whole number. And even the ones that have close to a whole number, we still show at least 2 decimal places, depending on the periodic table. Some periodic tables show more than 2, but most of them show at least 2 decimal places. And that's to specify our isotopes in the abundance. Now, we talked about a couple of classes ago, and that if we look at chlorine and we see that we have a mass of 35.45, and we know that 2 isotopes exist, chlorine 35 and chlorine 37, you can look at that mass and determine which is more abundant in nature, because the average is weighted for the thing that's more abundant in nature. So it's closer to the 35 than 37, so I know I have more 35 in nature. And if I actually had a couple of numbers, I can figure out how much more if I know some things. So that's where our abundance comes in. And again, it's just a matter of if there's hydrogen, and hydrogen with 0 neutrons is the most abundant isotope in nature, that's my mass I want to skew towards, because when I'm doing calculations with it, most of my hydrogen is going to have 0 neutrons. I might have a small percent that has 1 neutron or 2 neutrons, but a very little amount. So when I'm doing my calculations, I want my mass to represent that. So by knowing our natural abundance, we can have more clear calculations. So it's just a weighted average. This is all this is when you're looking at your atomic mass, is a weighted average to calculate your amount. So this little guy, if you have this in math, and if you're in calculus, you should recognize that, but if you're not, it's okay. It just means sum. So the sum of our fractional abundance of one isotope, how much is it found in nature, times the mass of that isotope, and then let's say I have 2 isotopes, I'm going to have 2 of these terms. The fractional abundance of isotope 1 times the mass of isotope 1 plus, that's that summation, the fractional abundance of isotope 2 times the mass of isotope 2. If I have 3 isotopes, I'll have 3 things I'm adding together. If I have 5, I'll have 5 things I'm adding together. So that's all that means, it's just a sum. That's what that symbol means. If we're given the fractional abundance of each isotope and the mass of each isotope, we can figure out our weighted atomic mass. So it's just a weighted average, just isn't really, you can memorize this equation, but if you understand what we're doing, what we're trying to figure out, you don't really need to memorize this equation. It makes sense. So multiplying our mass by our fractional abundance gives us our weight, how much that particular isotope contributes to our final average molecular weight. So let's do an example. So here we have an example where we have copper. And copper has, in this case, we're told 2 naturally occurring isotopes, copper 63 and copper 65. And we're given a mass of copper 63 and a mass of copper 65. And we're also given a percentage. So one big thing, though, we want our natural abundance. So in this case, it's not just given to us, we will have to calculate it. But once we calculate that, then we can apply it to our equation. So our first step, let's look at what we're given. We're given that copper 63, maybe. There we go. And we're given our percent. And that's our abundance, but it's in percent form, so we're going to have to convert it. And then, of course, we're also given our mass. And then we're also given our copper 65. And again, we're given our abundance. Oh, in this case, we're not given our abundance, but that's okay. We can calculate it. We have our mass of copper 65. So notice this is fractional abundance. So I want to convert my percent to a fraction. In other words, in the decimal place instead of in the percent. So that's really easy. What I'm not given is my abundance of copper 65. But if we only have two naturally occurring isotopes, that's not going to be very hard to calculate because I know some things about percentage. And if I know that I have 69.17% of one isotope, I can calculate how much percent I have of the other isotope. Because what is percent? Out of 100. So since we know it's out of 100, and we know we only have two naturally occurring isotopes, if I have 1%, I can calculate my other. So there's the two things we'll need to do. One is calculate my percent of copper 65, and two, convert those to our fractional abundance as opposed to our percent abundance. Because you will see that you won't get the correct answer if you leave it in the percent. Either way, it won't carry a unit because whether it's talking about a fraction or percent, we're still just talking about a piece of a whole. And we can say our whole is 100 because we're talking about percent. So it doesn't really matter. I'm going to calculate the percent of copper 65 first. Technically, you could convert it to a fraction, and then that'll be fraction of 1. So I'm going to do the percent first. So in 1, we know copper 63 is 69.17%. So to figure out copper 65, we know our fraction is of 100. So we can subtract 69.17% from 100, and that'll give us our percent of our copper 65. Everyone understands why that is? Again, it's just when we're talking about percent. Now, if we had 3 of those, we'd have to know a little bit more information. But we have only 2 isotopes. Now, we need to calculate our percentages to our fractional abundance. You can move the decimal place over 2, but just to be clear as I'm speaking about it, remember all our percent is our fraction over 100 times 100. So to calculate and convert that, our copper 63 is going to be 69.17% over 100. And that's going to give us our fraction. If you're showing your work, I don't necessarily need to see this, but you do need to show that you have converted it. I'm just showing that here so I'm clear that all we did was convert this from a percent to our fraction. So when we're talking about that, this is 0.6917 out of 1. And also note, if I take this and add this, I'll get 1, which I should because that makes sense, because altogether it'll equal to 1 whole. So you can always double check things. Now our last step is just to plug this into the fraction, into our equation. It's an easy mistake to make would be to pair this term with the wrong mass. So make sure your abundance of copper 63 is multiplied by your mass of copper 63. Don't switch them. That's an easy mistake to make. So again, notice how I wrote copper 63 so I don't lose what I'm doing when I'm doing this work, so I don't confuse myself. Because that's the easiest mistake to make with this one. So our atomic mass, I'm just going to put this as AM, is going to be equal to my fractional abundance. I'm just going to put Fa times my mass of copper 63 plus my Fa of copper 65 times my mass of copper 65. That's all that sigma sign means. So by plugging that in, I calculated my fractional abundance in fraction form, not percent. And I want to multiply that by my mass of copper 63. So I want to make sure I'm using the correct mass. Of course, it's the mass that's closest to 63. Because remember, that's what that 63 means. Plus the fractional abundance, in this case that I calculated, for copper 65 times my mass of copper 65. So when I plug that in, that's the first term. This is just for you to follow along later. This times this is going to give me 43.5353. This times this is going to give me 20.012772. As far as our significant figures, our fraction had to be measured. So this has 4 significant figures times 1, 2, 3, 4, 5, 6. Remember, we're multiplying, so that's our least number of significant figures. So that should be in 4 significant figures. This one has 4 significant figures times, again, 6. So our least number is 4, because we're multiplying. So when we add these two together, we should have 2 decimal places. Because when adding, we're going by decimal places. And of course, that's in atomic mass units, because this has no unit, this has AMU. So these both come out to AMU, and we can add AMUs. They have the same units. We won't really have that in any other unit. You don't necessarily, by showing your work, have to show this step. This is more for when everyone's looking back at your notes later. You're not like, where these numbers come from? So I broke it down a little bit. So fairly straightforward. And also, notice that we know that our abundance is more to our copper 63 because we have a higher percent of copper 63. So it makes sense that our AMU, our atomic mass unit that's calculated, is closer to 63 than 65. Because we know we have more of a percent of copper 63 based on what we were given. So you can always check that. If your number comes out to 68, well, that doesn't make sense. You did something wrong somewhere there, because your average should be somewhere between 63 and 65, closer to 63 because we have more of it. So that's how you can check this to make sure you're doing it right. If your number is nowhere near the max of 63 and 65, likely what you did wrong was not convert this to percent, or you might have switched these. So if you switch this abundance with copper 65, then your number would be closer to 65. So there's a couple of ways you can double check this, especially because you'll have multiple choice, so you can kind of look and have a good idea of what it should be. Your average should be somewhere averaged of your isotopes mass. So if it's like 0.5, clearly that's not right. Your average mass won't be 0.5. So a good way to follow these. I'm not going to go through this one right now. I want you to try to work on this one on your own. Because we're given our mass of our two isotopes. And I'm not giving you anything else, and I want you to calculate your percent abundance. And I'm giving you your average. So what you're not getting is your percent for either. So you're going to have to calculate that. A little bit of algebra will help you. So I'll go over that one on Friday, but I want you to work on that one on your own before I go over that one. And of course, this is going to be on the lecture when I upload it. You don't have to write it down now. But I want you to really think about this one because it's not as clear what you're not given. But remember, if you have two isotopes and you calculate the percent of one, you can easily find the percent of the other. But you have two unknowns here. So you're going to have to think about this a little bit, and we'll go over it on Friday. The next thing that we're going to talk about before we end this chapter is our atoms and how we visualize them and how we count them. So, if you may have noticed that the mass of every atom is different. So that gives us an issue when we're talking about atoms. However, we can apply a number for a mole of atoms, and that's how we'll typically talk about our atoms. The easiest way to relate this is, if I say I have a dozen of something, how many do I have? 12. Does that change if I have a dozen eggs versus a dozen elephants? No. No, but will they weigh the same? No. That's the same thing. We're talking about a really big number, but just relate this to a dozen. Dozen cookies, dozen eggs, different things. Eggs and cookies are not the same thing, but they both mean 12. So this is just a way for us to think about it. A mole of hydrogen isn't going to have the same mass as a mole of carbon because they have different atomic masses. They have a different amount of protons. They have a different amount of neutrons. They're different atoms. But a mole is going to always be the same amount. So we're going to discuss moles in this way. And usually we'll talk about moles as molecules, atoms, things. So just like 12 things is a dozen, 1 mole is equal to 6.02 times 10 to the 23rd things. Whether we're talking about a mole of elephants, we can talk about a mole of elephants. We can. 1 mole of elephants is 6.02 times 10 to the 23rd elephants. It's not going to have the same mass as 1 mole of hydrogen, but we can still talk about it that way. So this is Avogadro's number, and you have to know it. I'm not giving it to you. You have to know this number. Don't worry. If you do enough practice and you do your homework, you'll remember this number because we'll use it a lot. So 1 mole is equal to 6.022 times 10 to the 23rd things. Those things can be atoms, ions, molecules, elephants, whatever, they're things. For the most part, we'll be talking about atoms, ions, and molecules. But it depends what you're discussing. Where does that come from? Well, again, we had to normalize something. So a mole is equal to the number of particles. Number of particles equal to the number of atoms in 12 grams of carbon-12. Because remember, carbon-12 weighs 12 AMU. So that's just our normalization. That's where the number comes from. We had to have a way to normalize it. So that's why 1 mole of carbon-12 weighs exactly 12 grams. You don't need to memorize that. That's just where the number comes from. We needed some way to normalize it so we can understand it. What you do need to know is 1 mole is equal to Avogadro's number, and you need to know what that number is, which is 6.022 times 10 to the 23rd. So if you ever are confusing yourself, because that's such a big number, just think about dozen and relate it that way. And it's an easy way to visualize it, because oftentimes in chemistry we're working with things we cannot visualize. It's really small. So I always try to bring in a way for you to visualize it when you're thinking about it. So notice, if we have 1 mole equals 6.022 times 10 to the 23rd things, that's a relationship. And we know how to use relationships in conversions. So that's what we'll be talking about, using that in conversions. Also, from now on, atomic mass units, we are going to, because of carbon and the fact that 12.01 grams has 6.022 times 10 to the 23rd atoms, our mass units in our periodic table are always often considered grams per mole. That way we can, again, normalize it and visualize it. So that gives us another relationship between mole and our mass of our atoms and mole and our things. So anytime on the periodic table it says AMU, we can always think about it as whatever that mass is in grams per mole. Now we can convert that to milligrams, kilograms, things like that, which we've done, but we just looked at another relationship as well. So we'll look at some examples of this and using it in calculations. So the first thing is, if I want to know the number of atoms in a certain amount of moles of copper, I can do that. Again, here our things as atoms. If it was elephants, it would still be our things as elephants. So we are given 2.45 mole of copper. And I'm going to write copper because later on it's going to be really important that it's not just moles, but moles of copper. Right now it's not as important, but later on it will be, so I'm just going to be consistent. And we want to find how much atoms of copper that is. That was supposed to be in red. I don't know why I didn't do it. So things of copper. Now, as far as our conceptual plan, we know that we can convert moles to things because we have a relationship to that. And in this case, our things is atoms. So our relationship is simply our relationship that 1 mole of something is equal to Avogadro's number of things, and our things is atoms. So 6.022 times 10 to the 23rd. Please practice with whatever calculator you're using for quizzes and exams, because I can't go around and necessarily help you with your calculator if you're having a hard time with scientific notation. So make sure that when you're practicing your homework, you're using the calculator that you're going to use on the exams or quizzes. I can help with some of them, but you know, every calculator is different. I haven't played around with every calculator in the world. And we're going to be doing a lot with the scientific notation because I'm clearly not going to write out all these zeros. It would take a little while and you'd probably make a mistake. So that's our relationship. So our solution, and again, I'm going to write it out completely, 2.54 moles of copper. And our relationship says that for every mole of, in this case, copper, and I want our moles at the bottom so they can cancel out, we have 6.022 times 10 to the 23rd atoms of copper. Our moles cancel out of copper, so that leaves us with the units atoms of copper. We have 3 significant figures for our moles of copper that we were given, so our answer should be in 3 significant figures, and it is. we started with atoms, can we convert moles? And the answer is, of course we can. Also, our check. We know atoms are small, so a large number of atoms makes sense, because, of course, they're really small. What if we're starting with atoms, and we want to know how many moles? Well, we can do that. We can still just use the same relationship. And remember, just like a dozen is the same no matter what we're talking about, it's always 12. Our moles are the same no matter what we're talking about. Now, our mass is going to be different. That's based on our mass of the periodic table, but not our moles. So we're given the amount of atoms, 1.1 times 10 to the 22. Silver atoms, or things. Here, atoms are things. And we want to know our mole of silver. So again, here our conceptual plan is going to go from atoms of silver to our mole of silver. And we can do that because we have a relationship. Again, our relationship is 1 mole of whatever, in this case silver, is equals to 6.022 times 10 to the 23 atoms, and in this case we're talking about silver, or things. So in this case we're talking about atoms of silver. So we can set that up. We're starting with what we're given. But now, what goes on the bottom? Yep, so now our Avogadro's number goes on the bottom, so atoms can cancel out. So that means my mole goes on the top. When our, bless you, atoms cancel out, we're left with moles of silver. Mole is what we want our final answer to be in, so that's our calculation. Of course, we only started with how many significant figures? 2. So our final answer should be in 2 significant figures. Anytime you're using a relationship, if you're following your units, you won't make a mistake. So make sure you're writing your units down. It'll really help you, especially as we get more complicated. So as far as checking of that, number of atoms given is less than Avogadro's number, so that answer makes sense that it would be a negative, small number. I'm going to try to give you a minute for this one. Okay, I gave you a little bit more time for this one. I like this one because for some reason it confuses everyone. But remember what I said. We're just talking about things here. Get a little bit more time. purpose of a question like this is to make sure you're really understanding it. Because, I don't want you just to go through problems and do the same thing over and over again and not really understanding what you're doing. So if you can understand a question like this, and it's simple when we work through it, you'll see, then you really understand what we're trying to do by these discussions. But before we work through this one, let's talk a little bit about using the mass from the periodic table. So the mass of 1 mole of atoms is called our molar mass. That makes sense. 1 mole of atoms is our molar mass. And the molar mass of an element in grams is numerically equal to our atomic mass in AU. So if carbon is 12.01 AMU from the periodic table, then its molar mass, its mass per 1 mole, is 12.01 grams. So if we have 1 mole of carbon, we're going to have 12.01 grams of carbon. That's a lot of carbon, though, so we won't often be using that much carbon. If we talk about oxygen, which is 16.00, which means it's the most abundant isotope is oxygen 16, pretty clearly. We don't have any numbers. Then 1 mole of oxygen equals 16.00 grams of oxygen. So I don't really need to give you the molar mass. If you have a periodic table, you have the molar mass. That is the mass in grams per mole of that atom. So remember, the mass is under the elemental symbol of the periodic table. And again, this is why we want our mass to represent our fractional abundance, because if we had a sample of carbon and we knew it was a natural sample, so there's a fractional abundance there, we don't have to worry about which of the isotope masses we're using, because the average is based on the average. Now, if I knew I had carbon 13, I'd be using the mass of carbon 13. But typically, we're assuming we have an atom that contains the natural abundance of that molecule, of what's known. So this is just a review of that. Now notice that 1 mole of hydrogen has 1.008 grams of it, versus 1 mole of calcium is 40.08 grams. So it weighs a lot more to have 1 mole of calcium. Again, 12 eggs and 12 elephants don't have the same mass. So the lighter the atom, the less a mole weighs. That makes sense. Because again, we're just basically what we did is say for every 1 mole we have this many grams, so we normalize these. So we can use this as a relationship in calculations. So this is, I'll go through this one and the iClicker question. And then we're almost done with this chapter. So we're told that we have 0.0265 grams of carbon, and we want to know our moles of carbon. Our conceptual plan, we're going to take our grams of carbon and convert that to mole of carbon. Now our relationship, it's not given in the example, it might be, but we can find it because we can look on the periodic table. And the periodic table tells us that our molar mass is 12.01. So remember, that means, and that's a U, 12.01 grams per mole. So how is that a relationship? That tells me that 1 mole of carbon equals 12.01 grams of carbon. That's my relationship. For every 1 mole, I have this many grams. Now again, I'm writing carbon down because remember, I cannot use this relationship to calculate the mass of calcium because 1 mole of calcium does not have this mass. So this mass is specifically for carbon, so I'm being really clear with my units. So we start with the amount of grams of carbon that's given, and I can use this relationship and this relationship only to convert that to moles of carbon. So 13.5, well, I'm pulling a number out of anywhere, but 1.008 grams per mole would not work here because grams of carbon does not cancel out with grams of hydrogen. So that's why I'm keeping the carbon here to be really clear to myself that I'm using the right conversion. So that'll cancel out. We're left with moles of carbon on the top. That's what we want our final answer in. So that makes sense. We were given 3 significant figures in our math originally, so our final answer in moles should have 3 significant figures. This makes sense. It's a small number because, remember, 1 mole of carbon equals 12.01 grams, and we have less than 12.01 grams. So it makes sense that we have less than 1 mole. So we can use that understanding when we're working on this one. So for this one, I want to go over before I let you go today. I have 3 more minutes. Because I want to make sure one thing this will help you see what we're doing and have you understand it. Also kind of helps you a little bit with conversions. So it's not as hard as it seems like it would be. So first off, we're given 2 things. We're given the amount of moles of football that we're calculating. How many moles are we calculating? 1. So we're given 1 moles of football. Then we're also given our conversion because, of course, footballs isn't on the periodic table. So our conversion is a mass of 1 football is 0.43 kilograms. So that means 1 football equals our 0.43 kilograms. So that's our relationship, and that was given to us in our problem. We want to find our mass of 1 mole of football in grams. Of course, this is kilograms. So that gives us an extra layer of what we have to do. So we're starting with the amount of moles given, which is 1 mole. And I'm going to put this of FB just to save up room for this football. So remember, here we're given footballs. Footballs are things. What's our relationship between moles and things? Avogadro's number. So that's another relationship that wasn't explicitly given, but we need to recognize it. And in this case, things is footballs. So we have that conversion. 1 mole of football is equal to Avogadro's number. Of footballs. So that's our things. Now we also have a relationship that 1 thing, which is our football, is equal to 0.43 kilograms. So that would give us our mass in kilograms. Of course, we want our mass in grams. So remember, 1,000 grams equals to 1 kilogram. That's true of footballs, of anything. So it's a lot easier than what the problem made it sound like. And if you could do a problem like this, you're really understanding what you're doing. So of course, when you actually plug that in, it comes out to C. So we will finish this chapter on Friday. We don't have a lot left. Start on chapter 3. Y'all have a good day. Remember, your quiz is on Friday.
thank you for putting the thing on the internet.
It's helping?
Yeah, because I was doing homework the other night, and I vaguely remembered, and I looked at my